All right, good morning. We are still looking at special relativity, so let's get started. We spent a fair amount of time looking at how the predictions of special relativity, what they tell us about measuring distances and measuring time intervals, and we looked at a lot of interesting examples with those. And now we want to be able to move on and talk about energy, kinetic energy, and momentum formulas from special relativity. So we went over a number of examples at the last lecture, and I'm hoping you guys have had a chance to practice quite a few of those. Now, I feel like textbooks, this is one place where textbooks introduce some unnecessarily difficult formulas to work from. And you can decide. These formulas probably look a little different. I've kind of organized all these here. I've written down a whole series of formulas in terms of gammas and MC squared, whereas, and I've used gamma a lot. And textbooks, our textbook is good at introducing gamma. I feel like it could use it more. There are formulas that are simpler. Sometimes they're using formulas that are more complicated. Once you start having to do algebra with some of these problems. And so we may come back and talk about this some more. And I may... So there's a number of examples that we looked at. I think we finished up with this example from radioactive decay, which showed us that when radioactive decay occurs, there's enough of a mass difference that it's actually measurable, and that the reduction in mass shows up as a production of kinetic energy. And we stated too that in chemical reactions, the same thing's going on, but it's about 1,000,000 times less in terms of the energy produced in a chemical reaction, and as a result, the mass differences are so small that we tend to say that mass is conserved in chemical reactions, although that's not strictly true. All right, one more energy example from the chapter here, and the one that they've given us here is, it's a proton at the highest energy proton accelerator in the United States at Fermilab outside Chicago in Illinois. And it says that you can accelerate protons there to TeV, where T is tera, and tera is 10 to the 12th. And they want to know how fast are those protons going. So the large, now I didn't, the numbers I wrote down are not for the Fermilab accelerator. Instead, what I did is I did the Large Hadron Collider in Europe on the border of France and Switzerland at CERN. And maybe, I'm guessing it's more likely you've heard of the LHC. It's called the Large Hadron Collider. It's the most powerful accelerator on the planet right now. And the US, when I was in, boy, this goes back a ways, back when I was in graduate school, the US had started the construction of an even bigger collider, an accelerator in Texas. But at some point the US decided it was going to be too expensive and they shut down funding. So they're big tunnels. The one in Texas, I think, was going to be like 40 kilometers in diameter, or 50 or 60. And the one in Europe, this Large Hadron Collider, has a very large circumference to it. Anyway, the kinetic energies at the Large Hadron Collider are 6.5 TeV, so much higher than Fermilab in Chicago, but not as high as what was going to be called the superconducting super collider in Texas. So let's find out what the gamma factor is for those protons that are being accelerated. Now I'm going to use the formulas that I keep insisting are simpler to work from, that are shortcuts. And so I'm just going to use my kinetic energy formula, and I'm going to actually use that to solve for gamma. So gamma is equal to 1 plus k over mc squared. What I need to do then is put in my kinetic energy, which I've converted into MeV, 6.5 million, and then I put in the MeV mass for the proton. So the proton mass, and when we say proton mass, we typically mean mc squared. So very, very seldom do we work in terms of kilograms. We almost always work in terms of mc squared, and so the so-called mass is given in MeV. It's given in energy units. So this formula, the MeVs from the mass and the kinetic energy cancel, and I've got a gamma factor of 6,927. Now, the velocity, using my formula that we've looked at earlier, using that gamma, the speed turned out to be 0.9999990 something 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 times c. So again, the Large Hadron Collider uses protons and antiprotons and brings them up to high energy. Now, if you're at an energy of 6.5 million eV, you can create particles of that mass. You can take the kinetic energy from these protons, and when you run a reaction with the protons, sometimes you're going to generate higher mass particles. So you can discover new particles of higher mass that typically decay very rapidly, but we can verify their existence by looking at their decay particles. So the pattern of decay particles allows us to reconstruct the existence of these high mass particles. All right, so that's what's currently state-of-the-art in terms of a particle accelerator. Now, back when I was in graduate school and a postdoc at Lawrence Berkeley National Lab, our research group were involved in an experiment at the Stanford Linear Accelerator Center. So the group I was working with was part of a collaboration that included Stanford University and UC Berkeley faculty, UC San Diego, a number of University of Tokyo, University of Utrecht from the Netherlands. So there are just a lot of different research groups that formed this collaboration, probably 60 or 80 people involved. And that was back in 1993 when I graduated from UC Berkeley. And the kinetic energy of our electrons that we were using, Stanford Linear Accelerator Center does not use protons, they use electrons and anti-electrons instead. Now, the energies that you can get to with the electrons and anti-electrons, we've never gotten to these sorts of energies. On the other hand, in terms of how fast the electrons are going, the electrons back in 1993, at 1993 energies of those electrons was actually much higher than the protons are today at the LHC. The gamma factors are much higher, let's say. So because the electron is so much lighter, protons are like 1,800 times the mass of an electron. Because the electrons are so much lighter, the gamma factors that we work with are much higher. Our gamma factors were 28,376. And when you calculate the speed of those electrons, it was 0.99999999379 times c. So to measurable speeds, that's essentially c, right? Is how fast those electrons were going. Anyway, just an example that brings in some accelerator technology and gives you an idea of how much energy and how fast these particles are. All right, and at Stanford Linear Accelerator now, I'm not sure what energies they're running at now, but there was a time when they went from this 14.5, I know, and it's been some time back, they were at least at 50 GeV or higher, probably higher, 50 or 60 GeV. So they've run electrons at even higher gammas. Okay, so the formulas that we work with here, from relativity, they would work if we went back to physics 4a and use them back in physics 4a. We find that the formulas from Newtonian physics, from classical physics, are usually thought of as being a little easier to work with. So the formulas, and that's why in physics 4a, we go through the Newtonian approach to, or the classical approach to physics, rather than start right off with special relativity. But remember, the special relativity formulas work all the time. It's the Newtonian formulas that will only work as long as the speeds are low compared with the speed of light. Now, the chart here is saying there's no specific rule for when the speed is high enough. It just depends on the level of accuracy. For the level of accuracy we're looking to get in our calculations, we typically want to use relativity anytime the speeds become greater than about 10% of c. We can use them at lower speeds, but if we get higher than about 10% of c, the formulas from classical physics will start to give us important errors. We'll start to see that the numbers we're getting are off by, at least a few percent once we get up to those speeds. Okay, we said that in this next lecture, today's lecture, we would be looking at some of the more foundational mathematics of special relativity, and so let's do that. This is a picture showing that we are looking at two different reference systems. So we have two different reference systems here. We've got S, and we have reference system S prime, and we've got an XYZ coordinate system set up for each one, and we have a relative speed of v happening between the two reference systems. So the way we operate with these two different coordinate systems, moving at relative speed, we synchronize the two reference systems so that their origins overlap at t equals 0 and t prime equals 0. So that allows us to have these four-dimensional coordinate systems for both reference system S and reference system S prime, and to be able to keep track of how we switch back and forth between the two of them. In relativity, what we do is we take what we used to consider to be three-dimensional space and one-dimensional time and combine that into a four-dimensional space-time. So instead of working in terms of three-dimensional vectors, so in physics 4a, physics 4b, we always worked in terms of three-dimensional vectors. We would have x, y, and z coordinates of each vector or quantity. Now what we're going to have instead is, in addition to those three, we're going to have a time dimension to everything. So, and that starts right off with space and time. So it turns out that when we look at measuring distances x, y, and z, and then measuring time for a particular event, when we measure that from another reference frame, the time measurements get mixed together with the spatial measurements. So in some ways, I guess the way to state this is that what is measured as a time interval in one reference frame becomes a spatial interval in another reference frame. space and time get mixed together. It seems kind of crazy to say that. When I think about how I experience distance and how I experience the passage of time, they don't seem to be the same thing at all. And yet, mathematically they are. Now, they have been connected in classical physics. We've certainly connected space and time for hundreds of years. People have talked about setting up coordinate systems and measuring where something is located, and then also measuring the time at which something happens. So there's been an understanding that there's some connection here, but relativity says there is this deep mathematical connection that we have to take into account. Now, if we're going to create a four-dimensional space-time, that would tell us that we need something so that we can use the same set of units to measure space as we do when we're measuring time. Now, when we're measuring distances, when we're measuring space, we use meters. When we're measuring time, we're using seconds. Is there a conversion factor between the two? If time and space are somehow components of the same thing, then we really should be having the same set of units for both. So what we find is that there is a conversion factor between units of space and units of time, and the conversion factor is c. What we're used to calling the speed of light actually tells us how to convert space and time so that they can be treated as a four-dimensional vector. So along with z and y and x, what we introduce here is not t by itself, but we put a factor of c onto t so that we can compare compare the units of time and space. So with that, what it tells us is that 1 second of time is equal to 300 million meters of space. Now, I knew time was, 1 second was a long unit, but I didn't realize it was 300 million meters, but it is. That's not as easy to work with as maybe something else. We could work in terms of nanoseconds. Now, if I reduce c down to write it in terms of nanoseconds, it turns out that a nanosecond is equal to about 30 centimeters. So that's a conversion between nanoseconds and meters or centimeters. Is 1 nanosecond is the equivalent of 30 centimeters. Now, I wrote these equations here. I didn't really go into this much. We'll do this on the next slide or a couple slides in. These are actually, when I'm measuring distances and times in these two different reference frames, these are actually the conversion formulas that tell me if something is measured to have a certain distance and a certain passage of time in one frame, I can use those numbers to determine distances and intervals of time in another frame. Think in terms of that super fast train that we looked at. In that super fast train example, we said that the train had a certain length to it in one frame, and that there was a certain time interval as it passed through the tunnel. So I could take the length of the train and the time interval in one of these reference frames and use these two equations to calculate what the length would be and the time interval would be in a different reference frame. And if you can look at these formulas, this is gamma right here. It's this really pretty, kind of beautiful, symmetric relationship within special relativity as to how space and time are connected. All right, let's take another look at this. Now, In relativity, we work not from three-dimensional vectors, but we work from four-dimensional vectors. So the mathematics, kind of the foundational math of special relativity, is fundamentally four-dimensional. Now, we're not doing any of that in chapter 36. The textbook talks about it. We'll talk about it here in lecture some. But just to be aware that we use what are called four vectors. Now, the space-time four vector would mean measuring x, y, and z distances for an event or for something that's happening. And then we would also measure the time interval for that event. Again, you can think of some of those examples, maybe the super fast train, how we could move back and forth between the reference systems. Now, in the reference system that we set up here, we said the convention is to line up the x-axes in a way where the origins of the coordinate systems pass by each other, and also in a fashion where all of the relative velocity is exclusively in the x direction. Now, we could set up relative velocities in the y and z, but it just complicates our mathematics. So we could write down more general formulas for this. But we're going to go ahead and write down what's called the Lorentz transformation. So the Lorentz transformation that we've written down here is, well, I've written it in matrix form. Now, I'm hoping most of you have looked at matrices. You've taken linear algebra. The textbook does not use matrices for these. They just write them down as a series of formulas. And you know, it's fine either way. The matrix representation, if you understand how matrix multiplication works, can give you something that's more compact. But these four formulas here are the equivalent of this matrix formula that we have at the top. So what the Lorentz transformation does is it takes one four vector, again representing distances and time intervals, and it converts it from what would be measured in one frame to what would be measured in another reference frame. And so if in one frame we measure distances x, y, and z and time interval of ct, in the other frame we'll measure ct prime, x prime, y prime, and z prime. And carrying out matrix multiplication, let's see what the matrix looks like. Notice along the diagonal, for the y and the z, we just have ones. And that's because the length contraction effect, the time dilation effects that we have, are only related to the direction of motion along the x-axis, the formulas that we've been using. And so y and z are not involved in this. So a length measurement in the y and z directions will be the same in either reference frame. But measurements of time and measurements of distances in the x direction will be different. The other factors along the diagonal are factors of gamma, and then there's a couple of off-diagonal elements that are gamma times v over c. And what those tell us is, if you look at the formulas written down below, is when I switch from one frame to the other, this amount of time measured in one frame depends on the amount of time in the other frame, but it also depends on the position. It also depends on distances measured in the other frame, and then the whole thing gets multiplied by gamma. Okay, now the sign here, the plus and minus sign that we have here, those can be plus or minus depending on which way we're doing the transformation. If I'm going from measurements made in S prime over to S, and then I can take those measurements made in S and go back to S prime, what that will lead to is either a plus or a minus sign here. The sign in front of the velocities will reverse. And so if I take a Lorentz transform that looks like this, and then I take a second Lorentz transform matrix and put minus signs for the velocities and multiply those two transformations past each other, I get the unit matrix. I get ones on the diagonal. And what it's saying is a transformation from S to S prime and then S prime back to S. Those transformations are inverses of each other. And so the inverse transformation will undo the effects of the original transformation. And that's how the mathematics works with special relativity. Now, down at the bottom, I've written these out with the factors of C in place. Previously, we talked about, well, what would happen if I decided to define time units as meters? I know that 1 meter is the same thing as 3.33 nanoseconds. I could measure time in meters and distances in meters, and in that set of units, C then would become 1. So in four-dimensional space-time, where time and distances are measured in the same units, velocities are unitless. Velocities no longer have any units, and velocities run between 0 and 1, where 1 is the speed of light, and 0 is being at rest. So if we do that, then the C factors drop out. We no longer need this conversion factor of C, and that says that the formulas for the transformation look like this. And that, again, is that very clean-looking, symmetric mixing of space and time that special relativity tells us is going on when we switch from one reference to another. Okay, so let's try a few operations using this. So in addition to the position or the space-time 4-vector, there's a velocity 4-vector, there are acceleration 4-vectors, force becomes a 4-vector. Everything that was introduced as a vector in Physics 4a as a 3-dimensional vector is now going to be a 4-dimensional vector. Everything's going to pick up a time component. Now what's kind of interesting is when we look at momentum as a 4-vector, we can write down px, py, pz. Those are the 3 components of momentum that we're familiar with. The time component of momentum is energy, specifically total energy. Now, you know, a lot of students back in Physics 4a always comment that energy and momentum, they kind of have the same feel to them in some sense. Energy and momentum are all conserved quantities, and sure enough, your intuition is correct. Energy, or total energy, is the time component of momentum. So we can represent a particle's energy and momentum components all together as one 4-vector, and that's what it looks like in special relativity. Now, you guys know about dot products with, well, within physics and also within your math classes. If I take 2 vectors and I carry out a dot product operation, what a dot product does is it lines up all the components and multiplies the components of one vector with the corresponding components of another vector. Now, if I do a dot product with the same 4-vector, what we get is multiplying ct becomes ct squared, x squared, y squared, z squared. But when we work with 4 vectors, it turns out that the mathematics tells us that not all these signs are going to have the same sign to them. Some of these are going to be plus and some are going to be negative. So it turns out that spatial dimensions and time dimensions, when we put them into 4-vector notation, have opposite signs when we carry out the dot product. So, and it's easy enough to just write this down as I square the first component, but then I subtract off the squares of all the others. So when I take a dot product of a space-time interval 4-vector, it gives me something that's called the space-time interval. We don't use this a lot. It has a certain intuitive meaning to it, saying that it's taking into account both space and time distances. Now what it does tell us is that if I take a dot product, if I take the dot product of 2 vectors, that will give me a scalar quantity. Now in relativity, a scalar quantity, what's called a Lorentz scalar, is something that's measured to be the same value in every reference frame. So mass, for example, is a Lorentz scalar. It's something that's measured to be the same in every reference frame for an object. This space-time interval is also the same quantity in every reference frame. So if I take t squared minus x squared plus y squared plus z squared, if I subtract all those off, and then I move to another reference frame and do the same thing, the space-time interval is always the same in every frame. Even though the individual components, x, y, and z, and t, could be different. In general, they will be different. So let's take a look at the dot product for the momentum 4-vector. Dot product for the momentum 4-vector would look like this. It would look like squaring the e and then squaring each component of momentum and then adding the e squared but subtracting off all the momentum components. If I take px squared, py squared, pz squared and add those together, that will give me overall momentum. So the dot product gives me e squared minus pc squared. Now remember, a dot product is going to be a Lorentz scalar. It's going to be something that everyone agrees on in every reference frame. Well, it turns out that the dot product of momentum for an object is equal to its mass. And so mc squared, or m by itself, is a Lorentz scalar. And this is that fundamental formula that we talked about at the beginning of the chapter, maybe the second day, when we first started talking about energy. E squared minus pc squared is equal to mc squared squared. That's our general formula relating the mass, the momentum, and the energy of an object or of a fundamental particle. So let's see if we can derive these formulas with gamma that we talked about also back a day or so. What we could do is we could set up a Lorentz transformation. Now, the Lorentz transformation matrix doesn't just apply to space-time. The Lorentz transformation matrix that we introduced back here applies to every 4-vector. So if I have a set of velocities in a velocity 4-vector, accelerations, a set of forces, I can use the Lorentz transformation to transfer those components of any 4-vector into the components that occur in a different reference frame. So let's try that. What we can do is say that here is reference frame S, and here is reference frame S prime, and I'm going to take an object, I'm going to place it at rest in the S coordinate system. So with the object placed in that coordinate system, it has no momentum. It's at rest. So the momentum components for that would be 0, 0, and 0. Now it does have energy. So an object sitting there at rest has mass energy, So it has a total energy of mc squared. So that would be then the 4 vector for that object's 4 momentum measured in a reference frame where it's at rest. Now what happens if frame S prime measures that? Let's say that frame S relative to S prime is actually moving. And so if I'm in S prime, I don't see the object as being at rest, I see it moving. And I see it moving with a velocity v. Now, what we can do from that is we can set up our Lorentz matrix, our Lorentz transformation, and I can calculate in frame S prime how much energy will it have and how much momentum will it have. Now, I know that in the y and the z direction, it's not going to change, and that's because all of the relative motion, by convention, we've placed along the x-axis. So if I carry out the matrix multiplication on this, which I'm going to do now, I'm going to get E prime is equal to gamma times mc squared. Now I should have put primes in here, I apologize, I dropped the primes. But the energy that this particle will have measured in the other frame will be gamma times mc squared. So if there's a relative speed acting between these two reference systems, then whatever the speed of that object is in a given reference system, its energy can be calculated as gamma mc squared. For momentum, when I carry out the very same matrix operation, multiplication here, this is going to give me gamma v over c times mc squared. And so the momentum is going to be given by this other expression. And that's it. So the Lorentz transformation allows us to derive these formulas for energy and momentum. How much energy, how much momentum will I have for a moving particle or a moving object that has a mass of m. Okay, questions on any of that? So we've come back and we have derived some of our fundamental formulas that we started with to see where these are coming from. Let's go back and revisit, remember that super fast train that we had. So here is that super fast train, and it's moving. We're in the reference frame of the tunnel. So the tunnel is at rest. We'll call this reference frame S. Train is moving, its length contracted, and the train fits inside the tunnel. And if I look at event A and event B, the distance from the two ends of the tunnel, that's a distance of 200 meters. So those two events, there's a distance between them of 200 meters. Now what we found was that the train moving rapidly would just fit inside the tunnel. So if I ask how much time, how much of a time interval there is between event A and event B, those are simultaneous. There is no time difference. So in this reference frame, I have components of 200 meters of x and 0 seconds of time. Now, how is that going to convert over to the other reference frame? The other reference frame is where the train is at rest and the tunnel is moving. Now, let's use our formulas from the Lorentz transform to be able to go in and determine those values. So, if you remember, we had calculated the gamma factor here is 2.50, the relative speed between the two frames, 0.9165 times c. So I'm going to bring out my formulas that we got from the Lorentz transformation. I'm going to put in my factor of gamma. I'm going to put in my values of x and t. Now, t was 0, so that term drops out. But this term x, put in with the gamma factor, with that length contraction factor, brings us back to the length of the train. Tells us that the train length in its own reference frame will be 500 meters. Okay, so that's an example of using length contraction or showing how length contraction is built in to the Lorentz transformation. Now let's see how we're going to calculate how much of a time interval there is between event A and event B. Now, again, if we go back and look at the formula from the Lorentz transformation, we have a factor of gamma, have a factor of Ct, and we have this factor of V over C times x. Now, t is 0, so again, that drops out. And that says that the time difference between these events actually depends on the x value in the other frame. The time interval in the reference frame of the train comes from the distance interval in the reference frame of the tunnel. And putting those numbers in, 2.50, 0.9165, and 200 meters, gives us a CT value of 458 meters. Now, 458 meters of time, how many seconds of time is that? And to calculate that, we can put in, divide through by this factor of C. If we go back and look at the factor of C, 1 microsecond of time is the same thing as 300 meters. So light travels at 300 meters per microsecond. I'm using that as a conversion factor, and it tells me that the time interval is 1.53 microseconds. If we go back to that example that we looked at a few days back, so a couple of lectures back, that matches. So that works. The Lorentz transformation is correctly predicting how distances and time intervals in one frame are related to distances and time intervals in another. Now, if we go back to remember our dot product formula here and the space-time interval, we could do a space-time interval calculation. What we could do is we could take t squared and x squared and subtract it. And on this side, we could take t squared and x squared and subtract it. And what we would find is that t squared minus x squared is the same in both reference frames. There's a certain amount of space-time separation between these two events, and it would be measured to be the same in each frame. Okay, kind of interesting how that space-time connection works. Okay, questions on any of that? All right, let's move on towards, we're moving right along here, so I'm actually going to say this is our last topic for today's lecture. What we're going to do is look at the Doppler shift formula. Now, you guys may have heard of the Doppler effect. You've certainly, I'm guessing, you've heard of the Doppler effect for sound because we looked at it in Physics 4a. So if you were part of the physics going on here at Laney in the class way back, then anyway, wherever you've taken the physics course for Physics 4a, you've learned about the Doppler shift for sound. Light is not sound. I know that a lot of times there's an effort within physics and teaching of physics to try and draw the comparisons in a way where to point out the similarities, but I always like to point out the differences. Light's not sound. Okay? Light is not a medium in motion. Light consists of a bunch of fundamental particles, and those fundamental particles have very specific properties to them. So we do use some of the same mathematics to represent propagation of sound and propagation of light. They're not the same thing. Light's very different. So the Doppler effect for light is going to have a different, I feel like, a different fundamental foundation that it derives from. And let's think about this then. So let's say we have a beam of light. Here are all the photons moving along, and they're moving along at the speed of light, surprisingly. And I've got a couple different reference frames. Now, maybe the light source is in one of these reference frames, or maybe it's just a sample of light from somewhere else. But if I'm in one of these reference frames and I look over and I measure how fast the light's going past me, it's going by at c. And if this other frame looks over and measures how fast the light's traveling, they measure it going by at c also. Sounds like a contradiction, but all of the mathematics that we've gone through turns out to predict that whichever reference system we look at for light will always measure it traveling at the same speed. Now, the speed is always the same, but the energy and momentum is not. So as we move from one reference frame to another, the energy of the light, the energy of those photons, and the momentum of the photons will be measured to be a different quantity. Now, one way I like to think about this is if I'm standing on the street, if I'm standing out in the street, and a car is approaching me, and I go, that car looks like it has a certain amount of kinetic energy. What could I do to move to a different reference frame where the car has more kinetic energy, and I could run towards the car? So if I run towards the car, now in my frame, the car has more kinetic energy. If I run opposite the car and I look back, now in my reference frame, the car doesn't have as much kinetic energy. That effect does happen for light. So the speed's always measured to be the same, but the energies are different. If I look at a light source and I measure the energy of the photons of light that are coming by, if I now move in the direction towards the light where it's coming from, I will now measure the light to have more energy. And we call that a blue shift. Blue meaning the higher energy end of the visible spectrum. Now, I can turn that around. What I can do is I can look at where the light's coming from. I can move to a reference system moving away from the light at a faster speed, and that creates what's called a redshift. When I look over, the light doesn't have as much energy. So if you're running away from a light source and you look over and you see the light is still moving past you at c, and then you run faster and you look over and the light's still going by at c, you go, wow, no matter how fast I run, the light still goes past me at a speed of c. But what you can do is you can look over and measure the energy and go, oh, there really is a difference. As I run faster and faster away from the light, I look over and I realize the photons don't have as much energy as they used to. Okay? Even though they're going past me at the same speed, they don't have the same energy. Now, to calculate just how much energy those photons would have, how much of an effect is there in this Doppler shift for light, what we can do is come back to our Lorentz transformation matrix. Now, I've got to come up with a 4 momentum vector for my photons. Photons, remember, are massless, and that says that E equals PC and PC equals E. And that says that for a photon traveling in the positive x direction, its energy is E, that's just how much energy it has, but its momentum is also given by E, so I can write it this way. I can write it as E, E. Now, it doesn't have any momentum in the y direction, and it doesn't have any momentum in the z direction. How would I represent a photon moving in the negative x direction? So if the photon had the same energy, but it was moving in the negative x direction, then the energy would be unaffected, but the momentum would change sign. The momentum now would be negative E to show that it's going in the negative direction. Okay, if it were traveling in the y direction, then the E would be here, and the 0 would be up here. So this is the energy of light being measured in the S frame. And what I want to do is I want to measure now the energy of the light in the S prime frame. Now notice the S prime frame is moving faster towards the source of the light, and the S frame is moving away. So if S prime is going to measure a higher energy, is what it comes down to. This is moving more in this direction, and S is moving that way. S prime is moving more towards the source of the light. So I'm going to write down the matrix, or the 4-vector for my photons in frame S, and then I'll write down the 4-vector for my photons in frame S prime, and then I'm going to put the Lorentz transformation in between them, and then I'm going to cross my fingers and hope that the math works. So when I carry out the matrix calculation, I get E prime is equal to gamma times E plus gamma V over C times E. Now I can write that as E prime is equal to gamma times E plus gamma times V times C times E. I can factor out the E. I still have a factor of gamma, and I have a factor of 1 plus V over C. Now, that seems to have worked. I have a bit of a concern, and that is, what about the momentum? I know that for a photon, the energy and momentum should match, but if I carry out the calculation here, does it match? And it turns out it does. So you can try this. I didn't write it down separately, but I'm hoping if you do the matrix multiplication here, you can see that E prime is going to equal gamma V over C times E plus gamma times E. So it's consistent. So what behaves like a photon in one frame behaves like a photon in the other frame. It still has no mass. It still has an energy momentum that match. Okay, that's good. We're on the right track here, it looks like. Now what we can do is, let's see how those energies compare, because if I know how the energies compare, I know that the wavelength is going to depend on the energy and momentum. If I know what the energy is equal to, I can find out how the wavelengths also are affected by the Doppler shift, by measuring the light's property in a different reference frame. So I'm going to do some math here and a little bit of algebra. It turns out that gamma is 1 over 1 minus v squared over c squared to the half. Now, the denominator here is the difference of two squares. So that can be factored out into 1 minus v over c and 1 plus v over c. So I did a couple lines of algebra here. I multiplied top and bottom by some factors of c, and then I separated out that denominator using a difference of two squares. And then I factored the numerator out, the 1 plus v over c, and what I found was that I get a cancellation going on here. C plus v over c plus v cancels out. And what I'm left with is c plus v over c minus v to the half. Now you're asking, aha, what would have happened if we had transformed from here to here? What if we had gone the other direction? Well, if we had transformed the other direction, the off-diagonal elements in the Lorentz matrix would now have a minus sign on them. That would mean I would have a minus sign here and here, and that says that I would have minus signs here and here. And since I have minus signs here and here, the minus signs would cancel with the 1 in the denominator, and the minus signs and the plus signs in my formula would reverse. One of those is a blue shift, one of those is a red shift, depending on which direction I transfer back and forth between my two reference frames. All right, so here's the Doppler shift going on. Here is the formula. Now I'm going to call this the blue shift formula because the energy I measure, E prime, is higher in energy than it was in the other frame. This is my redshift formula for energy. It's got a minus sign here, and that's reminding us that the energy E is less than the energy E prime. Now, to convert this into wavelengths, wavelengths are given by hc over E, where h is Planck's constant. I don't know if we've introduced Planck's constant yet. We'll see that in the next chapter for sure. I think at least once or twice we've pointed this out back when we were introducing quantum mechanics. We definitely did. Now, what I can do then is I can take these formulas, and in place of E, I can substitute in hc over the wavelength. What have I done here? Yeah, okay. So I can plug in hc over the wavelength. E is equal to hc over lambda, so we plug those in. And now I have my blue shift formula. If I've got motion towards the light, the wavelength will be blue shifted. And if I'm moving away from the light will be red shifted. And we can use the blue shift and the red shift measurements to determine velocities. So we can find out how fast. We can look at a star or a galaxy, and we can look at how red shifted or blue shifted the light is and determine speed. You can also, with the Doppler effect, you can also be pulled over on the highway by the highway patrol, because that's what their radar guns work with. The radar gun sends out a bunch of photons, a radio signal, which is light, radio energy light, reflects off your car, and depending on what the energy of the returned photons is, they'll be able to tell whether you're traveling at speeds above the speed limit. So these Doppler shifts are really handy. We might as well toss this in. I think we're probably through for this lecture. Time to take a break. Yeah, let's do this quick. We'll probably come back and talk a little bit more about the Doppler effect. But so here's a good story. This driver claims that what happened was the driver got pulled over. I don't think the whole story's here. Yeah. Okay, so a driver goes through a red light, and a police officer pulls the person over. The person says, "Officer, what can I help you with?" And the police officer says, "Did you see that you just ran through a red light?" And the driver says, "The light was green. Oh, wait. Oh, it could have been a Doppler shift. You're right. It was a green light in my reference frame, so I really didn't go through a red light." And then the driver suggests to the officer that because it was a green light, they shouldn't be held responsible for going through the red light. But the officer had taken Physics 4C and did a quick calculation, and using the Doppler shift formula, the officer was able to go through the Doppler shift formula and solve that for V, and write that in terms of the wavelength, kind of a typical wavelength for a red traffic light or a green traffic light, and plug in the wavelengths for those lights, and find out that the driver was speeding at 0.382 times C. So the driver got a speeding ticket, which is, $50 for every 5 miles an hour over the speed limit. Anyway, good story with the Doppler shift. We'll stop there. It's time to take a break, and then we'll come back and wrap things up.